Okay, so in this second part in the series about the LED strip lights, I'm going to go into greater detail on the construction of the LED tapes themselves, both different types that I have. And to do that, I'll show you under a microscope how both of the tapes work, and I'll lay out the circuit path and how they're constructed. Okay, we'll see you there. Okay, everybody. This is the part where we'll go into deeper detail about the construction of the two different types of LED strips or tapes that I purchased. On this sketch pad here, or graph pad, I've sketched out the basic layout of the components that make it up, and you can see in the video, the microscope video, I've got the power pads for the plus and minus rails, the first LED package, current limiting resistor LED package, two more current limiting resistors LED package, and then the voltage pads at the end again. And in the bottom tape, same thing, voltage pads, LED package, current resistor, LED package, current limiting resistor, LED package, and then the voltage pads again. So that's the configuration. And what we're going to do here is we'll power it up and we'll trace the circuit, the way that those components are wired up. But before I go into that, I mentioned earlier that the upper tape, this one here, is what I would refer to as inferior. The quality of the light isn't as good. It's more of a 5,000, 5,500, maybe even 6,000 Kelvin temperature, even though the advertising for it was like 4,000 to 4,500. And right now, the way it comes from the factory, and I'll show you a piece of it like that, it has this kind of rubberized plastic coating over it because I guess it's waterproof or water resistant. And you can see when I turn it on the side, it's it's I guess it's pretty optically okay. So it might not be a problem from an optical standpoint, but wiring this sucker up, especially if you cut the 5 meter tape into 10 or 15 or 20 pieces and then hook them up in parallel, you've got to cut off the segments at the ends, on both ends, cut off the plastic, the rubber stuff, to get access to the electrical pads. And it's a pain in the rear end, let me tell you. So in addition to the quality not being great as far as the light output, the actual lumen output isn't as good as the bottom tape. I just don't like it as much. And the bottom tape is the newer one that I prefer, which has a genuine light output in the 4,000, 4,500 range. And you can see the configuration is different. So what we're going to do here, we'll power it up and we'll look at how that is different. And just to one more overview, I have a camera looking at the sketch pad. I have another camera, the microscope camera, looking at the tapes, and I have my GoPro basically looking at the voltmeter so that you could see what the voltages are as I probe them. So let me turn the power supply on, and currently I only have it at 7.5 volts. And let me up that just a little bit. Alright, so what you see there is the upper LED strip, although it looks like it has 3 LEDs, actually has 9. Each one of those packages has 3 separate LEDs. And if you notice, each of those packages has 3 pins on the bottom and 3 pins on the top. So 6 pins altogether versus the bottom, which just has the 2 pins. So it's really 9 LEDs and 3 resistors versus the bottom, which has 3 LEDs and 2 resistors. So we'll go through that, and the way we'll lay this out, I'll turn up the voltage so it's easier to see what the voltage drops and whatnot, and then we'll just lay out on my sketch pad what the voltages are at each point so we can trace how the circuit is wired. So let me up this to 10 volts. Much brighter. Okay, and we'll start with the bottom. So Probing the bottom minus power pad, and I'm showing basically 300, 200 microvolts, so less than a millivolt. And then the plus DC pad, I'm showing basically just under 10 volts. And that's the case with both wire strips, LED strips. They're both powered from the same power source. So that's the minus bus, the ground side, if you will, and you can see what the voltage is. So let me go to the bottom of this LED and see what the voltage is. So that's showing basically ground, telling me that the bottom of this LED is connected to ground. And the top of it, I'm showing 2.7 volts. So 2.700 volts. So let me write that down. 2.700, and the bottom was 0. Okay. So let's go to the LED, the resistor next to it. I show 3.400 volts on the bottom. 3.400, and at the top of that I'm showing 2.700. 2.700. So what's interesting is the voltage is higher at the bottom than at the top, and it also shows that the voltage at the top of the resistor is the same as the top of the LED. So that's telling me that the top of the LED and this top of this resistor are tied together. Alright, let's go to the next LED. And at the bottom I'm showing 3.400 volts. 3.400 volts. And at the top of it, 6.475 volts. 6.475 volts. So I think you can see already that the bottoms are connected from there to there. Alright, let's go to the next resistor. And I show 2.716 at the bottom. Let me double check, see if I read that correctly. 7.216. Knew that couldn't be right. And then at the top of that I get 6.475. 6.475. So once again you see the connection at the top of the LED and resistor. So going to the last LED, I show 7.217. 7.217, and the top should be basically VCC, or the top. So 9.994. 9.994, and let's just double check the voltages at the output rail there. So at the bottom I'm showing basically 0, and at the top I'm showing 9.994. Kind of pretty much as you would expect. So 0 and 9.994. So schematically it looks to me that we're connected like that. Then the top of the LED goes over to the top of the resistor. Then it comes out of there, goes over to the bottom of the next LED. Then it comes out over to the top of the next resistor. Then down over to the next LED, and then finally over to VCC. So that's the kind of circuitous route that it takes. So you have 5 components, 3 LEDs, 2 resistors, in one series circuit, and that's a 50 millimeter piece of the LED tape. So the next 50 millimeters would have another group exactly like that, and again you would have another 5 component string in series connected to the bus. So basically you have parallel groups at each 50 millimeter segment. Now the top tape is a different story altogether. Again, first of all we'll verify the VCC, and again 0 volts and 9.994, 995. But now, because we have the 3 contacts here, we need to take 3 voltages for each LED. So starting with this section there, I got 0, 0, and 0. So the first side there was not going to be much veneer, so we'll just write that as a 0. The top is going to be a bit more complicated, I'm afraid. So I get 2.938, 2.938, then 2.932, 2.932, and the last one for this package, 2.935. 2.935. Alright, well, let's check out this resistor. So at the bottom of it, I got 4.089. So 4.089. And at the top, is it going to be higher or lower? And it's lower. 2.935. 2.935. I think we can see possibly how that might be connected. Alright, let's go to the next LED. So starting at the bottom, left hand pin, 2.937, 2.937. Next one, 2.931, 2.931, and the last one of the right hand side, 4.089. That's interesting, is it not? 4.089. Look at that. Look at that. Alright, we'll come back to that. So, top left hand side, 5.901, 5.901, 5.889, 5.890, 5.890, and the last one is 7.055. 7.055. Okay, so 2 more resistors. Bottom left hand one, 7.059, 7.059, and the one beside it, 7.054, 7.054, and at the top, 5.889, 5.889, and 5.900. 5.900. Okay, and let's go to the last LED package, again starting at the bottom left. 7.053, 7.053, 7.057, 7.057, and the right hand one, 7.053, 7.053, and we'll go to the top left, 9.995. Again, we're looking at the plus rail on this. 9.995. 9.995 and 9.995. No point in writing that all down. We'll just double check the bus to be sure. So 0 and 9.995. 0 and 9.995. Okay, so again, this is a more complicated circuit, and what we're seeing basically is 3 LEDs in each LED package, and they're not tied together in any way. They're basically tied to the other LED packages. Kind of interesting the way they do that. So the voltage that sticks out at me here on this first resistor is the bottom of it, 4.089, and that matches with this over here. So I'm going to come over and say that that's what works out. And let's see, 2.935, that I'm pretty sure is this first, or the third one I should say. Then it's kind of hard to write that with it, so I'll label this as A, and we'll label this as B. So I'm going to say A goes to here. So this is A, and B goes to here. 937, 938, 931, 932. So those are the appropriate voltages. Now, since this guy has gone through a resistor, the third LED in the group has already gone through a resistor. It's not going to go through any of the other resistors. So this is going to be tied to, well, it looks like 705, 3. It could be this one or that one. I'm pretty sure it's this one here. But let's look how this goes here. 5.900, 5.901. That's how this goes. And 5.890, 5.889. Definitely it goes like that. So that goes there for sure. So 7.054, what? 59 goes to 57, I'm pretty sure. So it looks like it goes like that. And then basically this guy here gets tied to here. So essentially, if we have A, B, C, A, B, C, A, B, C as the LEDs in each package, A goes to A, B goes to B, goes to B, C goes to C, goes to C, and then ultimately at the minus side here, they're all tied. They're all tied here to the minus, and then all tied here to the plus. So that's how that circuit works. And again, it's a more complicated circuit. So basically, LED C goes through this first current limiting resistor. So I'll write that as C. And then this one's B, and this one's A. Or at least that's how I make it out. Okay, last little bit on this. I'm going to show you something about the way these tapes consume power, the current they draw. So let me up the voltage to 12 volts, make it a little easier to see. And at 12 volts, both tapes combined are drawing a little over a watt, and we're right at 100 milliamps as the current draw. So two different tapes, same length, 3 LEDs each. So are they drawing the same amount of current? Well, let's see. Let me unplug one of the tapes and see what the current does. Again, right now we're at 100 milliamps, so if I unplug one, we're down to 65 milliamps. So, nope, they're not drawing the same amount of current. The top one is drawing 35 milliamps, and the bottom one is drawing 65 milliamps. So, not quite double. Not quite double. And it's been my experience in using these tapes over, basically longer segments of them, that the bottom tape does in fact draw more current, though not in aggregate, 80% more than the top one as it appears here. Remember, in a small sample size with just 3 LEDs in each tape, you can get a substantial variation. The turn-on voltage for these LEDs and the current they draw individually is not a constant. There's sample variations, and if you have just 3 LEDs, you could have a group of 3 LEDs that tend to be on the current hungry side, or 3 that might be on the current not so hungry side. So you can skew the results a little bit by having a small sample size of just the 3 LEDs. But again, it's been my experience that the bottom tape does in fact draw more current and puts out more light. So it's not just consuming more power, it does in fact put out more light. Alright, let's take a look at turn-on voltage to see where that happens. So let me go down to 7 volts. And let me turn off this light here and turn this light down. And it's hard to tell there, but let me up the voltage just a little bit. There we go. You can see the bottom one starting to come on. You don't notice the top one so much, but we're less than 7.2 volts. Okay, now you can see the top one start to come on, and we're not quite 7.3 volts. So there's definitely a difference. And one of the things here that's quite interesting is at low voltages like this, the actual current flow, and you can see on the power supply, I'm showing 0 milliamps and 0 watts, even though I'm at 7.3 volts. That's because the current is in the microamp range. And this resistor here, I'm showing 2.401 volts at the top and 2.401 volts at the bottom. So basically 0 voltage, or almost 0 voltage drop across it. So again, very little current flow. That's a 24 ohm resistor, as I recall. And similarly at the top, 2.426 versus 2.426. So again, essentially almost no current flowing through this guy, and I have to check to see what the resistance value is on that. So turn on voltage and the voltage drop across the LED is not a constant. Let me turn the lights back on again so you can see better. So voltage drop across an LED is not a constant. They're rated at a certain voltage drop, but that voltage drop is dependent on the current that flows through it. Again, looking at this first LED, I'm showing 0 volts at the bottom and 2.401 volts at the top. And if I go to 12 volts, much brighter, at the bottom I'm showing not quite 1 millivolt, and at the top 2.77 volts. So I mean a substantial difference in the voltage drop across the LED. And so it's not a linear relationship where the voltage drop across it is linear with the current. It's more of an exponential deal where the current increases much faster than the voltage drop increase. Alright, let me drop this down to 8 volts. Makes it a little easier to see. So, one other factor to keep in mind is that the way these tapes are constructed, you can see at the end here this voltage rail pad. This is the plus one, obviously, and then the minus. So that looks to be about maybe a little bit more than 2 millimeters wide. Same with the minus side. And I believe that this pad basically runs the entire length of the tape in parallel fashion. The plus rail and the minus rail run the length of the tape, and you know, it's a thin foil of copper, and then there's a layer of plastic on top of that, insulating it from the interconnect layer that goes between the LEDs and resistors in each 50mm group, ultimately tying to the plus rail at one end and to the minus rail at the other end. But this kind of highlights why we have this voltage drop problem. You know, to make these tapes flexible, they make those copper pads or strips, the rails, as thin as possible. And also, copper's not cheap, so, you know, trying to save money, they'll use as little copper as possible. But the bottom line to that is, if you've got a 5-meter stretch of tape and you're pumping 12 volts into one end of it, the accumulated current draw of all of those 50mm groups over 5 meters means that there's quite a bit of current draw through basically conductors that are not very beefy. So you get a lot of voltage drop. In fact, with 12 volts input at one end, you'd be lucky to see 9.8 volts at the other end. That's how much voltage drop there is. But, you know, it's a combination of the need to make them inexpensively, so they use very little copper, and the need also to make them, you know, foldable and flexible and coilable. You know, if those were beefy conductors, you wouldn't be able to do that so well. So that's sort of the trade-off you have in a design like this.